Okay, so here we are. We received our ultrasonic transducer here. Okay, so 40 kilohertz, and now we need a 40 kilohertz of frequency to drive this, but I don't have a circuit, the driver circuit for this. When we talk about the signaling frequencies, what we have here, okay, for instance, if we supply a voltage to a transducer, and we have a switch here, this is our transducer here, and this is our switch here. So if we tap the switch like 3 times in a second, it will be around 3 hertz. Okay, in a 3 taps per second will be around 3 hertz. Okay, so but this will not drive, this will not create the resonance in the transducer. These transducers work differently. Like if we tap it 3 times, it will not create a resonance in this transducer. So the reason why it will not create the resonance here, it's because they are like a capacitor, the 2 plates parallel to each other, so they will store the charge. So even if we tap it, it will not, create the resonance because of the charge. The voltage will remain same here, whatever the voltage here, okay, because of the capacitance, the static charge build up on this plates of the transducer. So what we have to do here is we need to find some other way to do it. We need to discharge this capacitor at the same time in order to drive this resonance of a frequency here. So the easiest way to do it is to put a MOSFET or a transistor here, and this MOSFET or transducer will consist of a gate, and it will have a drain, and it will have a source. So if we provide a signal at the gate, it will short these 2 wires, okay, and we need to keep the switch on, and we need to provide a signal here, okay, the tapping frequency here, okay. So what it will do is it will provide the voltage, and when you provide a signal here, it will short these 2 wires and disconnect and discharge the transducer also. So but this will create a lot of reverse energy because of the shortage. The amperage will be very high, so we need to put a resistor here, okay, most probably like 2 ohm resistor, or maybe 3 watts. So this resistor will when it will be shorted on the signal, this resistor will handle the load, okay, so it will not burn up the circuit. And this signal will be provided by a function generator, okay. So function generator are also very expensive these days, We will figure out the way to do it. So now the idea is to use this. This is a PWM signal generator. It is same as a function generator. Basically it provides voltage on a frequency here, and you have a duty cycles here. Okay, so this PWM circuit is very useful. Let me show you guys how it works. You will just simply have to provide a voltage supply here. Let me connect the supply. Wait. Okay, so here we have our voltage. Let me increase it to 12 volts. It was on 5 volts previously. And let me find a small LED light to check it. Okay, now so the LED light will be connected to the positive. On the positive side, negative. I'm just trying to show you how the signaling works, the pulses, how the pulses work here. And we need to see the, oh sorry, this is somehow reversed. I put the blue wire in the positive mistakenly, so it's okay. As long as I know, it's okay. So here we can see the light is glowing, and we have a 50% duty cycle. Duty cycles means that if this kind of square wave is generated by this signal generator, and this is the width of the duty cycle. Oh, sorry for my messy table. Everything is useful on my table, but still it's messy. So this is my duty cycle, and this is the frequency. Okay, if this per if it fluctuates 3 times per second, it will be 3 hertz. That's how it works. So these are the frequency counters, and we have this. Now let me show you how it works. This is 1 hertz. See, the 1 hertz means it is pulsing every second. See, 3 hertz mean it is pulsing 3 times a second. And it's fun. Wow. See, at 48 it is pulsing so fast that we are not able to notice the pulsing. But if I reduce it, see, now I can feel the pulsing here. I'm not sure if you can see it on my video, but there's a slight fluctuation in pulsing, and now it is visible more. See the pulsing. This is how it works. So this transducer works on 40 kilohertz. Okay, and this 40 kilohertz transducer is getting the resonance of 40 kilohertz. Like this is 28 kilohertz, 40 kilohertz. No, this is 28 hertz, and this is 40 kilohertz. 40 kilohertz means 40,000 hertz. So if we provide 40,000 hertz of electricity of signaling here, it will resonate. Okay, so this is how it works. So my idea is to use this function generator to supply voltage here. But the problem is the voltage is too low to drive the gate. Or maybe I'm wrong. Let me check it with the transistor here. Yeah, here we have it, a transistor. Let's check it. Let's make a small circuit. We need to put let's put the LED on it. So this is the drain here. I will just temporarily connect it to see if it works. It will work obviously, but let's see. So we have this is a gate, this is drain, and this is source. I put a resistor here to remove any static charge buildup in the gate. Basically what it does, if you when you supply the gate, it will keep it turned on. Even if you remove the gate voltage, it will remain on. So if you put a resistor here, this will quickly discharge this MOSFET and only short these two wires on when you supply the gate current. So we have the drain here. We need a positive voltage here on this side. Okay. Okay, and this will be the negative. It looks a bit complex, but it is very simple. Basically, this drain pin in this upper part metallic structure is same, you know, that's why I connected the drain here. And now if I keep the frequency low to a readable state, for instance 9, now let's see if I supply here. Oh, see, this is working. It is basically working. Alright, now let's see if it has a good amount of current to drive a relay or something like that. Let's see. Let me find some small relay. Oh, I always find something useful in my mess. I extracted this relay from somewhere, and let's see if we can oh no, we have to supply voltage from somewhere else. It will not directly run the relay, but if it can drive the transistor. Yeah, see, it doesn't have enough current to run the relay. But if I connect this, the LED is working because it is taking a very low amperage, so that's why it's working. But it is not able to drive the relay with this pulsing. So let me find some other way to do it. Okay, let me make a connection first. Okay, so I just wired up everything. Now let me show you guys how it works. So we'll keep the duty cycle to 50%, and this is the relay which I connected here. I'm supplying the relay directly from this 12-volt supply here. This is a 12-volt supply. So how is it working? I use this MOSFET here, okay, to drive this relay. Okay, the positive part of this signal generator is directly connected to the gate of this MOSFET, and this relay is being derived from these 12 volt, and the negative side of this 12 volt is supplied to the MOSFET, and the drain of this MOSFET is connected to this relay. Now you must be hearing the clicking sound here of the relay, which is directly in synchronization with the LED light. If I increase it, you can hear that. In our project to create the drive circuit for this transducer doesn't involve any relay, because the relay can only support up to 100 Hertz, not more than that, and this transducer is working at 40 kilohertz. So the problem is that the relays cannot be used in this project. I'm just connecting relay here just to demonstrate how the signal generator can be used to create a circuit for this transducer, but we cannot use a relay because relays are limited to these are limited to 100 Hertz of frequency. They cannot go more than this. Let me show you guys. See, it is still resonating, but see, after this is 79, this is 84, 91, 102. Oh, it's still working. 151, but now see at 195 it is not it is not working as efficiently, because it is vibrating too fast and the electrical contacts inside them will not connect properly. So that's why we cannot use the relays. We will be using MOSFETs like this, again in a series here, to drive this ultrasonic transducer. So let's get back to work now. I hope you guys understand how we are proceeding to make this ultrasonic cleaner circuit to drive this transducer. Okay. Okay, now we will proceed to create a circuit for this 40 kilohertz transducer. Now I will pause the video now and assemble a circuit to drive this ultrasonic transducer. Okay, so I disconnected everything. Now I will make a transducer circuit here. So we have our supply of voltage, okay, which will be going to a MOSFET. This is a MOSFET here. This is drain, this is gate, and this is source here, and this MOSFET, and here we have a transducer here, ultrasonic. I will try to be as clear as possible. I'm thinking too fast, that's why I'm unable to write and draw very quickly. Sorry for the handwriting. So here we have what we need here is a function generator also. This is a function generator FG. This function generator is this circuit which I was talking about. Okay, this circuit is a function generator. The positive input is connected here, the negative input is connected here of the function generator, and the output of the function generator will go if this is the positive PWM signal and this is the negative PWM signal. The positive will go directly to our gate. Okay, and as we discussed earlier, we need we will put a big resistor here, and this will connect our ultrasonic transducer. Okay, there will be two terminals of the transducer here, and now the thing will be like this. Okay, what we will do is we will connect the positive to this ultrasonic transducer, and we will be so this is the voltage directly supplied here. Now the function generator will be used to short the circuit here to create a resonance here. Okay, so for that what we will do is we will connect the drain to one terminal of the transducer and source to other. The source will be connected to the other transducer. Right now I am using the transistor, the MOSFET here, and this MOSFET is basically IRFP4115. IRFP4115 right now. It was around 150 volt, and the gate voltage is around plus minus 20 volts. So I'm using it here to drive this. Okay, so what we're gonna do is the function generator will be connected here, the positive will be connected here, and the negative is basically common, so you don't need to worry about the negative one. So now what are we doing here now? Okay, and we will also connect an LED here with the function generator negative point and the positive point. We will connect light emitting what do you call it, like this. Okay, and this LED will we don't need an LED because at 40 kilohertz it will not be blinking or pulsing, but we can connect it anyway just to see if the circuit is working. But what we have to do here is we need to connect a fuse also somewhere in the circuit. I think one fuse should be connected here, and another fuse should be connected to the gate here. Okay, these two fuses are required. That in case the MOSFET is shorted, it will not destroy our function generator. The fuse will be blown on the reverse voltage. We will measure how the fuse will be. We will calculate about the fuse, about the safety ratings of the fuse, and then we will install it. And one thing we forgot here, we also need to put a resistor between gate and source in order to avoid the static charge buildup in the MOSFET here. So this resistor will be I don't have space. Where should I draw? Here. This will be around 10 kilo ohms. Okay, just to avoid the static charge buildup in the MOSFET. And this function generator will be adjusted to 40 kilohertz or whatever your transducer is. It will be set like this. Okay, so I think it's a very dirty diagram I made, but let's build a circuit for this again and let's see if it's work or not. Okay, now let me pause the video and proceed with it. Okay, so I pretty much assembled this circuit. I use a bulb here instead of this resistor. I don't have this resistor here, which I mentioned for the protection. So instead I use this 12-volt bulb for the excess return voltage. It will be consumed here. So, and I wired up this MOSFET here like the diagram. I use the source and drain connected to the transducer and also connected to the main supply here. But one thing I need to do here right now, before powering up the circuit, I need to set my function generator to supply a frequency of up to 40 kilohertz. It will take a lot of time to set it up to 40 kilohertz because right now it's 1 kilohertz, 2, 3. Oh, that's a little bit poor. I'm sorry, my stand is a bit flimsy right now.
How you get wet?
Oops. Wait, let me set it to 40. I subtracted and I mistakenly set it beyond 40. So here we are at 40. Okay, we'll keep it at exact 40. Okay, so this is the positive here. I will connect this and it should work. Oh no. Maybe it's not working quite nicely. Okay, so we are sending the signals here. Wait, let me see. Oh, it is not vibrating because maybe we don't have enough voltage supply. Oh, I need to see what is the supply voltage for this transducer here. Should be written somewhere in my 40 kilohertz, 60 volt, piezoelectric. Not written anywhere. Guys, keep it low. Okay, so I cannot see if I can find the voltage supply. Let me see. Okay, so as per ChatGPT, we have we asked a question here about the resonating supply voltage, which is provided from the drive circuit. So it's saying that this ultrasonic transducer here is drive on the voltage of around 100 to 150 volts. Okay, so 100 to 150 volt of a resonating voltage will drive this transducer here. So, and I'm also thinking to rework on this circuit because it is consuming too much power, and that is why this light bulb is glowing, although it's an oscillating voltage. I kept it at 1 hertz and still it's glowing. Like right now it's on 5 volt. I reduced this system voltage to the 5 volts and still it's not providing the pulses as it should. Regarding this this basic circuit design I made initially, this circuit design was basically I got an advice from an electronic engineer. He told me to put a MOSFET in this direction. I was skeptical about this design because it was shorting the circuit. So it obviously it will use too much energy. So now I'm thinking to use this MOSFET in the series as a relay to turn on this MOSFET, and I will use same 10 kilo ohm resistor in parallel with the transducer to remove the static charge buildup on the transducer. So let me try that design, because let me be honest, I'm not an electrical engineer or electronics engineer. I am an art student, I'm an architect, I design buildings, and this is my hobby to do this circuit designing and repairings. So I think I should go with my own idea of building this circuit by using this MOSFET in series to drive this transducer, and then let's see if it works. And I also need to increase the voltage to 100 to 150 volts. So I'll make another part of this video to do that. Meanwhile, let me design a circuit as I was thinking to make. So here we have a supply voltage. So we need a MOSFET here. So we have drain, gate, and source here. So we will use the function generator as usual. Our wire will be connected to the function generator, and the function generator positive wire will be connected to the gate here. Okay, the function generator will be supplying the voltage of around it will just supply it will just drive the gate of this MOSFET. And then for our transducer here, what we need to do is we need to provide a steady voltage. This will be connected directly to the one point of transducer, and the other will be supplied from the drain of this MOSFET. So drain is thing, so I will connect the drain here. Okay, and the source will be connected to the negative voltage here. Okay, so what it will do is it will work as a relay. This MOSFET will turn on and off this at 40 kilohertz, and to avoid the static charge buildup, I will put maybe first I will try with 10 kilo ohms resistor here in parallel with the transducer. So initially this was my idea, but the electronic engineer advised me to do this by shorting the both terminal through the MOSFET, but I'm quite skeptical about how it is working. But let's see, maybe it's I'm making some mistake here. And this is, and about this one, this is my initial idea to how to make it. And regarding the static charge buildup, I didn't know that the ultrasonic transducer make their own store their own static charge. So for after that information, the electronic engineer, he's my friend, he advised me to go with this design. So maybe I should put a resistor here to discharge this static charge buildup and then proceed with it. So let me design one more time again, and let's see. First I will try this, and if it still doesn't work, then we will go to the part 2 of this video. Okay, it's already been 40 minutes since I'm recording. Okay, so I'll pause the video again. Okay, so I just assembled everything again in this series circuit as per this design. And now let's try again by connecting the power here. Okay, well, so we have a blink here in the LED light. It means the voltage is going directly to the transducer right now, but right now it is 5 volts. Let me increase the frequency. Also, I will reduce the duty cycles. Okay, so we have now basically this LED light is right now connected in parallel with the transducer here, and this transducer is basically working directly on 5 volt right now, and right now it's not oscillating. If it's oscillate, it will there will be a bit of sharp noise come from that, so we will increase it to, I put this LED here just to check if we are receiving a signal on the transducer. We will set the main voltage later, but right now I'm just trying to see if the circuit is operating or working properly or not. Right now I might not be able to drive this transducer, but I need to see if we are providing the correct oscillation or not, and we will keep it at first let me put it the 12 volt again. Now it's on 12 volt. The light is also brighter. Oh, I already hear something from the ultrasonic transducer. Let me keep it at, I'm not sure if you guys can hear on the camera, but now it is I can hear the sound from the coming from the transducer. Although I forgot to connect the resistor between the terminals of the transducer. Maybe so it's 40 kilohertz. No, I cannot hear anything. Maybe right now we don't have enough voltage, but I can feel it working. I can feel it working. We need a higher voltage to drive this transducer now, because right now it's a very less voltage. If it drives on 100 and 150 volt, at least the circuit is working right now. I can see the circuit is working right now, because previously it didn't even vibrated or made any noise, but right now when I was setting the frequency, so before 20 kilohertz it was putting out some kind of noise, and now after 20 kilohertz it's not putting out any noise, but it is oscillating very lightly. So if we provide proper voltage, it may now oscillate properly. So video to experiment with this ultrasonic transducer, and now in the next video I will be supplying it with the 100 volt, and we will make it work now. And the idea of making this video is to make a very cheap transducer circuit using this signal generator, function generator, and I believe it's now working. The idea is working. The circuit is more simpler now, and now it is working better than this design. So I should be, next time I will be understanding the circuit on my own. I will never be taking advice from any electronics engineer unless I don't have any idea on what should be done. If I have any idea, then I will be working on my own circuits, designing my own circuits. So now we'll make it work in the next video. Thank you guys, thank you for watching. I hope we learned something from this video. The idea is to experiment and to do things that are that can be done in a better way. So obviously in the completed circuit, in the final circuit, we will be also using inductors and capacitors to supply the voltage properly, and we'll make a proper circuit here to keep it working. But the idea will be to keep the circuit at a minimum cost. This module is about $1 only. It only costs $1. Okay, and same goes for this MOSFET here. This is you can find 2 or 3 of these MOSFETs in $1. So only maybe up to $3. We will keep the budget of up to $3, and then we will design the circuit to keep it working properly and to see that if it's possible. Okay guys, thank you for watching. Goodbye.